Hello everyone. Today I'm going to discuss on another important reaction called as Oppanauer oxidation. So before we go into the actual details of Oppanauer oxidation, let us know what is Oppanauer oxidation, what is a general reaction for this one, followed by the mechanism of Oppanauer oxidation. Okay, so straight away we'll go for the definition for this Oppanauer oxidation. So it is nothing but oxidation of secondary alcohols into ketones in the presence of a ketone and a base, okay, is known as Oppanauer oxidation. So in simple terms, if you want to understand, Oppanauer oxidation is nothing but oxidation of secondary alcohols into ketones in the presence of a ketone and a base is known as Oppanauer oxidation. Okay, so we are going to convert a secondary alcohol into a ketone. That is the main objective of Oppanauer oxidation. Now, commonly used ketones in this reaction, I will give you a list of ketones. Okay, so we can use any of these ketones in Oppanauer oxidation, like acetone, methyl ethyl ketone, and cyclohexanone. So among these three ketones, we can select any one of them to convert a secondary alcohol into a ketone. Similarly, what are the bases we are going to use in Oppanauer oxidation? I list out the bases also, like aluminum tertiary butoxide, next potassium tertiary butoxide, and aluminum isopropoxide. Okay, so these are the most commonly used ketones and bases used in Oppanauer oxidation to convert a secondary alcohol into a ketone. These are the primary requirements of your Oppanauer oxidation. Okay, so next we'll see what is a general reaction involved in this Oppanauer oxidation. Okay. Right. Coming to the reaction of Oppanauer oxidation. So I'll take one secondary alcohol here. This is a general structure of secondary alcohol. And I'm going to react in the presence of a ketone. I'm going to select acetone here, which is the simplest ketone. And this reaction can be done in the presence of aluminum tertiary butoxide, aluminum tertiary butoxide. And you know this aluminum tertiary butoxide will act as a base. Okay, So what is the final compound you're going to get? So you're going to form a ketone once again. So I'll put and write the product here. R, C double bond O. So this is ketone plus you are going to get one alcohol derivative also, CH3, CHOH, CH3. Okay, so usually this is called as 2-propanol. This is the byproduct you are going to get in Oppanauer oxidation. So this is a general reaction. I'm going to take one secondary alcohol, react with ketone. So I'm going to take acetone as an ketone here. In the presence of a base like aluminum tertiary bidoxide, you are going to get a ketone plus 2-propanol as a byproduct. Okay, so this secondary alcohol has been converted into a ketone here. But if I say like this, you may not be able to understand. So to discuss this reaction in a more elaborative way, we'll have the mechanism of Oppanauer oxidation, where exactly you can understand how this secondary alcohols are converted into a ketones. Okay, so I'll just erase this reactions here so I can explain the mechanism of Oppanauer oxidation very elaborately. And well, mechanism of Oppanauer oxidation. So listen carefully. To simplify this mechanism, I will explain in 2 steps. Okay, we can complete in single step also, but for your convenience and easy to understand, I will divide this mechanism of Oppanauer oxidation into 2 steps. Okay, step number 1. Formation of aluminum derivative of secondary alcohol. Okay, so I'm going to write the structure of secondary alcohol once again. RCHOH R dash. So this is your secondary alcohol. And to understand the mechanism, okay, I will try to write the OH in this way. Just to understand the mechanism, okay. Plus, I'm going to react this secondary alcohol first with a base. What is the base we are going to take? Aluminum tertiary butoxide. Aluminum tertiary butoxide, right? Now, initially, what happens is, due to the electronegativity difference between oxygen and hydrogen, oxygen will get more electronegativity. Therefore, when you break the bond between oxygen and hydrogen, the electrons will shift towards oxygen, and therefore oxygen will get 3 lone pair of electrons. Originally, oxygen will have only 2, but these electrons present in the sigma bond also migrates towards oxygen, making it an additional lone pair of electron. What happens to this hydrogen here? Hydrogen will get a positive charge. Okay. Now, this aluminum will get a positive charge here, okay, and this entire tertiary beta oxide group will get a negative charge because aluminum will have least electronegativity, okay. So therefore you can designate by a positive charge. Fine. Now what happens is, to stabilize or to nullify the positive charge on aluminum, oxygen will donate the electrons for aluminum. Why? Because oxygen is having 3 lone pair of electrons. So this extra lone pair of electron, it will donate for aluminum, which is having a positive charge. Therefore, what happens? A new bond will be formed between oxygen and aluminum. Okay, now you can see the structure. R, CH, R dash, the same thing I have written here, followed by oxygen. Okay, now this oxygen, as it is donating the electrons for aluminum, you will get a new sigma bond like this, aluminum, okay, followed by okay. Now this positively charged hydrogen combines with one tertiary beta oxide group, okay, to liberate a byproduct called as, so here Me refers to methyl group, okay. Me is nothing but the methyl group. So here oxygen is having negative charge, so this negatively charged oxygen will take up this positively charged hydrogen to form OH, okay. So you will get three methyl groups here, CH3, CH3, CH3. So this is tertiary butanol. This is a byproduct in step number 1. Okay, and this is called as your aluminum derivative of secondary alcohol. I hope the step number 1 is clear. Okay, so let's move on to the step number 2 now. Okay, in step number 1, it is nothing but the formation of aluminum derivative of secondary alcohol, where you are going to react secondary alcohol with aluminum tertiary beta oxide. Okay, so you are going to get this aluminum derivative along with tertiary butanol as a byproduct. Okay, so next, coming to the step number 2. So step number 2 is nothing but your formation of your product, that is formation of ketones and 2-propanol. This is nothing but your byproduct. Okay. So let me erase all these things, so I can explain you the step number 2, which is the most important step because we are going to form the product now, ketone. Okay, now I will draw the same structure what you got in step number 1, that is aluminum derivative of secondary alcohol, R, C, H, R dash. Just to understand the mechanism, I'm writing in this way: oxygen, aluminum, okay. So this I'm going to react with acetone, CH3, C double bond O, CH3. This is your acetone. Okay. Now, how this aluminum derivative of secondary alcohol is going to react with acetone is most important. You have to understand now. So first thing, you compare the electronegativities of carbon and oxygen in acetone structure. You know, oxygen is more electronegative, right? So this pi bond will migrate towards oxygen as it is having highest electronegativity. So originally oxygen will have two lone pair of electrons, right? So when this pi bond is shifted to oxygen, oxygen will get additional one more lone pair of electron. So what happens to this carbon here? Carbon will get a positive charge. So carbon containing a positive charge, you can also call it as carbocation. Okay, so carbocation has been generated in acetone structure, right? Now we need to stabilize this carbocation now. Okay, now to stabilize this carbocation, so this particular structure, aluminum derivative is very, very important here now. So first thing what I will do is, I will break the bond between oxygen and aluminum. You know that oxygen will have more electronegativity. So when you break the sigma bond, the electrons will come out and migrates towards oxygen, which again, it will get additional one more lone pair of electron. Okay. Similarly, if you now I will break the bond between carbon and hydrogen. Okay, so what happens is the electrons will be taken up by hydrogen atom, and this hydrogen will get a negative charge. So this negatively charged hydrogen will migrate towards the positively charged carbon. Therefore, this carbon can form a new sigma bond with this hydrogen. So this hydrogen containing a negative charge, you can call it as hydride ion or hydride anion. Okay, so when hydride anion is transferred towards the carbocation, this is also called as hydride anion transfer. Okay, so what happens to this carbon here? Carbon will get positive charge. How carbon got positive charge? Because when you break the bond, immediately this hydrogen has taken away the electrons and donated for this carbocation. Therefore, this hydride anion can form a new bond with the carbon atom. That's the reason this carbon has got positive charge. This positively charged carbon you can stabilize very easily. You can nullify the positive charge on carbon by oxygen. Because oxygen is having extra one lone pair of electron, it will donate here to carbon. So this carbon can form a double bond. Okay, so you will get R, C, R dash. Here you are going to get double bond and oxygen. This is nothing but your ketone. Okay, plus now here aluminum is having positive charge, right? Here in acetone structure, oxygen is having 3 lone pair of electrons. So 1 lone pair of electron you can donate for aluminum. Therefore, this oxygen will form a new bond with aluminum. Okay, so we can write in this way: aluminum, oxygen, CME3, and this aluminum is going to form a bond with oxygen. Okay, followed by, so when you transfer this pi bond towards oxygen, you will get only single bond like this, carbon. Okay, next, this hydride ion has been transferred to this positively charged carbon. So you can write CH directly, followed by 2 methyl groups. These 2 methyl groups. Okay, now to get 2-propanol as a byproduct, already we got the main product, ketone is completed. Okay, so we got ketone perfectly here without any problem. So we should get another byproduct, that is 2-propanol. Now this compound you can subject it for hydrolysis, aqueous hydrolysis. So you will get H plus ion and OH minus, right? When water is dissociated, you will get H plus and OH minus. Okay, so I will try to break the bond between aluminium and oxygen. Therefore, what happens? The sigma electrons will migrate towards oxygen. So originally oxygen will have two lone pair of electrons. When you break the bond, the electrons will come out and migrate towards oxygen. So oxygen will get additional lone pair of electron. Okay, so this additional lone pair of electron, it will donate for this H plus. So oxygen can form a new bond with H plus. So you can get the byproduct also here. Directly you can write OH followed by CH, CH3, CH3. Okay, this is called as 2-propanol. Okay, so this is your second step where the aluminum derivative of secondary alcohol has been converted into ketone. Okay, and once ketone is formed, okay, you can consider this as a major product. And apart from this, you are also going to get this aluminum derivative where you are going to break the bond between aluminum and oxygen. It will have 3 lone pair of electrons and it is subjected for aqueous hydrolysis. So this H plus ions will be generated from water molecule and this H plus will be taken up by oxygen to form OH. This particular product, you can call it as 2-propanol, which is a byproduct in your Oppanauer oxidation. Okay, so this is a 2-step mechanism to understand the Oppanauer oxidation reaction. Okay, so thank you. In my next video, I'll explain few more important reactions of synthetic importance. Thank you very much.